Hey everybody, Dr. Retzik here with you. This is our sixth and final video in section 7a. Here we are continuing our discussion of normal operators. Let's get started. So we're going to round out 7a by working through 3 virtues of normality. They're short and sweet, but they are wildly important to us moving forward into 7b, and they start to give you a feeling that, oh, okay, yeah, normal operators, this is where it's at. Okay, so for the entire discussion, here's the setup. It's our classic situation. We got an inner product space V. We got an operator T, takes inputs from V, produces outputs in V. T is not necessarily self-adjoint, but it does have the nice feature that it's normal. So T star comes out the same as T star T. Okay, so that's what we know. The 3 virtues begin with the virtue that was alluded to at the end of the last video. Part of being normal is, yeah, T and T star don't do the same thing to V, but at the very least, the norm of TV and the norm of T star V agree. And not only that, it's an if and only if. So fact number 1, T is normal if and only if norm of TV equals norm T star V for all V in V. Okay, let's prove this. Let's actually practice together doing proofs with these normal operators. So here's the proof. Let's do this direction first. So let's assume T is normal. Okay, well, that means, so T star is the same as T star T. Thus, okay, let's figure this out here. So if you were interested in the norm of TV, you would be just as well interested in the norm of TV squared, and that's an inner product of TV with TV, which is inner product T star T V with V by properties of adjoint. That's how the adjoint works. But T star T is T star, that's by supposition, T is normal. And then by definition of adjoint, that's T star V, and that's nothing other than the square of the norm of T star V. Sweet. So if it's normal, then norm TV and norm T star V have to match. Okay, we're good that direction. All right, now, in the reverse direction, let's suppose that norm TV equals norm T star V for all V in V. Okay, and now we need to argue that T is normal. Here's how the argument goes. We want Tt star to be the same as T star T. So we will argue that Tt star take away T star T is the zero operator. Now, here's a little added morsel. When you're working with normal operators, or operators just generally, if you look at this difference, Tt star take away T star T, that operator, that whole thing, is self-adjoint. Now, that's not a mysterious thing, but it takes an observation to believe. So let's make this little argument here. Tt star take away T star T, all starred? Well, that's the star of this, take away the star of that. But remember, the star of ST is T star S star. So the star of this is T star star, T star. But T star star is T. Meanwhile, the star of the second piece is T star star. But T star star is T. So you see that this operator, Tt star take away T star T, that whole thing, that's self-adjoint. Now, the reason we want to take note of that fact, since Tt star take away T star T is self-adjoint, always, in any circumstance. That's what we just proved in the blue. By, I think it was theorem 716, but it doesn't really matter what the theorem number was. Remember, for self-adjoint operators, if TV always ends up orthogonal to V, when T is self-adjoint, then T must have been the zero operator. So all we have to show is that Tt star minus T star T acting on V comes out orthogonal to V itself. And that will prove that this self-adjoint operator, Tt star minus T star T, is the zero operator, which is what we were trying to show. We need only show that Tt star take away T star T acting on V, inner product V equals 0 for all V in V. And this is this first moment where sort of one of those little technical theorems about self-adjoint operators all of a sudden becomes useful to us because we're applying that theorem to the self-adjoint operator Tt star minus T star T. Okay, let's do the algebra now. But we can just do this out. Let's do it. But Tt star minus T star T acting on V, inner product V, that equals Tt star acting on V, inner product V, minus T star T, V, inner product V. That's what additivity in the first slot. that's just a general inner product thing. Of course, this one is T star V, because that's how adjoints work. You get to just move this guy, whoop, and pay with a T star. And similarly, this one then is TV, inner product TV, same story. Just take this guy and move it into the second slot, pay with a star. And oh, look at that, isn't that nice? That's the square of the norm of T star V minus the square of the norm of TV. And in this direction of the proof, those norms are equal. So that is indeed 0. Thus, by 7/16, T star, take away T star T, is the 0 operator. In other words, T is normal. So we've done it. Now don't lose sight of the forest for the trees. This was virtue number 1 of being normal, and that virtue is an operator is normal if and only if norm TV and norm T star V always match. Okay, now we're going to really get rolling. Once you have virtue number 1, then virtue number 2 comes easily. Okay, so check this out. Virtue number 2, if T is normal, then T and T star have the same eigenvectors. So this is great. When T is normal, T and its adjoint have the same eigenvectors. They don't necessarily go with the same eigenvalues, but they have the same eigenvectors. Okay, so let's see if we can prove this. Proof. Okay, suppose V in our inner product space has TV equal to lambda V. Okay, then we want to show that T star V is also a multiple of V. And the multiple, you might guess, is not lambda V again, but lambda bar V. So let's see what we can do here. Let's see. Oh, hang on a sec. Sorry about that, everybody. Domestic issue. Okay, we're back. All right, where were we? So if T is normal, then T and T star have the same eigenvectors, which is really nice. Okay, so we say suppose V is an eigenvector for T, so TV equals some scalar multiple of V. So let's say TV equals lambda V. In that case, 0 is equal to the norm of T minus lambda I acting on V. That's not a mysterious thing. T minus lambda IV, that's 0, because TV is equal to lambda V. All right, but T minus lambda I is also normal when T is. So since T minus lambda I is normal, then norm T minus lambda I acting on V is equal to norm T minus lambda I star acting on V. So this equal sign right here, this is because T normal implies t minus lambda I is normal. You can check that just by starring stuff and multiplying things out. In any case, t minus lambda I is a normal operator. So the norm of t minus lambda I acting on V is the same as the norm of t minus lambda I star acting on V. Of course, we know how to star stuff. So this is nothing other than t star take away lambda bar I acting on V. In other words, t star V must equal lambda bar V. And that's it. So if V is an eigenvector that goes with an eigenvalue lambda for t, then it's also an eigenvector for t star, and it goes with eigenvalue lambda bar. Fantastic. So normal operators, t and t star have the same eigenvectors. And the eigenvalues aren't that different. They're just conjugates of one another. Okay, virtue number 3. Virtue number 3, and this one is huge for us moving into 7b. This virtue is extremely winning. All right, last virtue. If t is normal, then eigenvectors that go with distinct eigenvalues are orthogonal. This lends great structure to the study of normal operators. Okay, here's the proof. Proof. Suppose t of u equals alpha u and tv equals beta v with alpha not equal to beta. Okay, now we want to argue that u and v are orthogonal. Here's the argument. Alpha minus beta times inner product u with v. Okay, let's see if we can multiply this out. So that's alpha times uv, take away beta times uv, because that's how scalar multiplication works. Remember, this is all happening in a field. So definitely, these are all just numbers right now. So you can definitely distribute. Okay, and then in the first one, let's decide to put the alpha with the u in that first slot. And then in the second one, let's decide to put the beta with the v in the second slot. So we know we can do that. By putting it in that second slot as a beta conjugate. Okay, now let's regroup. we're trying to figure out how to argue that U and V are orthogonal. So we would like it if this whole expression came out to 0. Because if the whole expression came out to 0, then the quantity we started with is equal to 0. But it's not the parenthetical term's fault, because remember, alpha and beta are different. So alpha minus beta is not 0. So if that product in the dashed line comes out 0, it has to be because U and V inner product came out 0. Okay, so let's see what we can do here. So this is TU with V, and this one is U, and then I think we just figured out this is second slot. Is this T star V? Let's make sure we have that argument right. V is an eigenvector for T. By virtue number 2, directly above this one, T and T star have the same eigenvectors. And not only that, you can see how they're related. So if V is an eigenvector for T, it's also an eigenvector for T star with the conjugate eigenvalue. We're using that right here. Because T is normal, and because TV equals beta times V, we get for free from virtue number 2 that T star V is beta bar V. Of course, we know what this second term is by definition of adjoint. That second inner product is just TU inner product V. So the whole thing is 0. And since this piece, by supposition, is not 0, we have shown that the inner product of U and V is 0. So that's it. Those are the 3 virtues to review. T is normal, if and only if norm TV and norm T star V match. If T is normal, then T and T star have the exact same eigenvectors with eigenvalues related by complex conjugate. And if T is normal, eigenvectors corresponding to distinct eigenvalues are necessarily orthogonal to one another. All right, that's it for 7a. We have put down the foundation that will allow us to go into 7b and start to see the structure of these operators. Okay, I'll see you soon. Bye.